you. Okay. Okay, great. Okay, yeah, so my name's Sasha. I work on the same experiment as Simon, but today I'll tell you about some work kind of using it in a different modality of more analog simulation rather than gate-based. So as we all know, kind of are starting to have the opportunity to experimentally probe quantum phenomena, and as Soon-Won alluded to, kind of start to discover new physics in these synthetic platforms. And there's several approaches you can kind of think of taking. So firstly, kind of the more standard, like continuous analog evolution. So you have some simulator, it has some native Hamiltonian, and then you can study the physics of that. And this comes with advantages such as easily reaching large system sizes. Typically, your Hamiltonian will be stabilized by energy gaps and dissipation. You are, however, limited to specific models and often have few checks or constraints in place to kind of make sure you're doing what you intend to be doing. Then on the other end of the spectrum, you have this kind of digitized approach, and for example, using error-corrected approaches for simulation, and these are highly programmable. You can use error mitigation techniques to ensure you're really very precise in what you're doing. It does, however, come at this huge cost of like complex control and very high overheads. And between kind of these two ends of the spectrum, you have other approaches. So for example, Floquet engineering in the analog sense, or as Simon was talking about, gate-based, but with physical qubits, so you kind of lower your cost a little bit. And so kind of focusing more on this like analog approach, in the last decade or so, many different platforms have started to develop these tunable simulators, which can access a really large range of Hamiltonians. But typically, you don't have ways of like ensuring that you're doing what you want to be doing. So it's difficult to know that you've precisely targeted the dynamics that you're aiming for. And so, as I mentioned, we're working with this Rydberg simulator, and it's kind of able to access this entire scale. So we can go from like the analog continuous evolution in the ground Rydberg manifold, for example, all the way to these digitized operations. And so on the left side, you can study, for example, phases of matter of the native Ising-type Hamiltonian. And then if you go into the PXP approximation, so in the limit of strong blockade, this now applies some constraints. So now you really constrain your dynamics to this subspace of the Hilbert space, which in some sense is now giving you this constraint and this way of checking that you're doing what you want to be doing. So this is what we want to utilize and kind of see how far along this spectrum can we take the analog evolution and use these constraints. So, okay, like kind of what's special about Rydberg blockade? Typically, if you do a quench, you would think your state thermalizes. We know quite a few examples where that doesn't happen, so integrable systems or with many-body localization. In Rydberg atoms in particular, kind of also as Soon-Won mentioned yesterday, you have this phenomenon of many-body scars. So because of the kinetic constraint of blockade, you get this like non-thermalizing dynamics, and here, as shown in like 2017 for the first time, you get persistent revivals of crystalline order after a quench. And further, kind of in 2021, shown that you can stabilize these like scarred trajectories using periodic driving. And this is an example of like this robust dynamics within this constrained space. And so the idea of the work that I'm going to talk about is kind of can we leverage this robustness and now perturb around these many-body echoes or like periodic revivals and use this to robustly engineer some Floquet Hamiltonian. And so, okay, a lot of this theory work should be attributed to Naz and Johannes, and Naz is here, so definitely talk to her if you're interested. But the basic idea, so we start off with the Rydberg Hamiltonian in the PXP approximation, and then apply some periodic detuning drive. So first, essentially a series of pi pulses. So you evolve under PXP, then under minus PXP, such that at stroboscopic times, you come back to your initial state, and therefore your stroboscopic effective Hamiltonian is just identity. You do nothing. Now, okay, yeah, in experiment, kind of this is what it looks like. You have some complicated micromotion, but then at periodic times, you come back to the same state. Then if you add some perturbations on top of this detuning drive, you can generate some slight deviations away from this many-body trajectory and pick up some effective evolution at stroboscopic times and generate this effective Floquet Hamiltonian. And now we can think about combining the programmability of like the platform, for example, tunable geometry or initial state preparation, with this ability to generate some effective Hamiltonian. So as a first example, kind of a very ubiquitous Hamiltonian, which is just a hopping Hamiltonian. So engineer a chemical potential term, some spin exchange or hopping, crucially within the blockaded subspace. That's what the P projectors are. And then also it has some next nearest neighbor interactions, which aren't super important, but they're there. And then, so yeah, the plot shows kind of what the detuning drive looks like. And what we can do, we can take our spin chain, prepare a spin in the middle, and then watch it hop. And kind of this is what you get. And as you tune here the epsilon parameter in the detuning drive, that tunes your hopping energy, and you can see you go from essentially a static spin to like several hopping times. And this is a good signature that we're implementing a hopping Hamiltonian, but kind of you want to be sure that you're doing what you think you're doing. So naively, you can just compare to a simulation of the kind of Floquet ansatz and extract some hopping energy. You can also be a bit more clever and use your experimental data combined with some ansatz to do Hamiltonian learning and extract not just the hopping energy, but also the chemical potential and effective dephasing terms. And then, okay, so that's like using ansatz. We also maybe want to like probe the system and like study its properties without a priori knowing anything about it. And for that, you kind of do some spectroscopy. And here we look specifically at the band structure, so looking at the dispersion of this single particle. And you can do this by Ramsey interferometry, the basic idea being you prepare your spin in a superposition state, you allow it to evolve, and then you measure in the x basis, and this gives you off-diagonal correlators, which, from which you get the Green's function in real space and time. From that, taking the Fourier transform, you get the spectral function. And then, okay, this is what it looks like. You have here shown the real part of the Green's function, and you see this kind of cosine-like dispersion corresponding to the single particle dispersion that we all know and love of kind of a tight binding model. And from that, you extract, again, the chemical potential and the hopping energy, and find, crucially, they're extremely consistent also with the kind of Hamiltonian learning technique from the previous slide. So this really gives you confidence that you're doing what you intend to be doing. And now we can go a little bit further to more complicated models. So firstly, looking at the scattering interaction. So as I said, this is a hopping Hamiltonian, but within the blockaded subspace, which means that it's now an interacting spin model. They don't map to free fermions because of the blockade. And so if you put two spins next to each other and allow them to hop, they can't both hop onto the same site. And this gives you a scattering interaction. So if you compare this kind of quantum warp profile with the quantum warp profiles of the individual spins, you see this modification in the density profile, and in particular here see this effective repulsive interaction because of the blockade in the Rydberg picture, which is the scattering interaction in the spin picture. And then, so going beyond single spins, you can instead go to the high density limit and look at domain wall physics. So here have also added, crucially, this like GPXP term to the effective Hamiltonian. So we're now allowing for weak spin flips as well as the like prior hopping Hamiltonian. And now if you start from some antiferromagnetic Z2 state and flip a spin, this creates a pair of domain walls which can propagate. And similar to the single particle case, these have kind of a cosine-like dispersion. The crucial difference being that now your vacuum state is not just all ground, but it's this two degenerate Z2 and Z2 prime states, which kind of changes the physics quite significantly. So one experiment you can do is you can prepare this initial Z2 state and then weakly couple that to the domain wall band by allowing for this small g spin flip term, and then scanning the chemical potential of this Z2 state relative to this domain wall band, you can see where you resonantly couple. So here that's like around this like minus 0.05 chemical potential value, and see that you resonantly create domain walls as shown by this dip in the Rydberg density. And this has also an interesting interpretation in terms of like a dynamical probe of the underlying ground state phase diagram. So there turns out to be a Luttinger liquid phase, which is exactly described by gapless domain walls, and that's kind of the same physics that this simple picture is probing, and it was also very related to what Antoine was talking about in terms of Luttinger liquids. And okay, to kind of summarize this Hamiltonian is we have the ability to engineer these short-range hopping interactions, and you can now think about like putting it on other lattices, for example, and studying various other settings. Okay, but moving forward, I think one of the really powerful things about this Floquet approach is it allows you to generate like truly arbitrary or almost arbitrary Hamiltonians, and in particular to generate multi-body interactions. So two-body kind of, you can find natively in many platforms. For example, optical lattices can definitely do hopping like better than this can, but the multi-body terms is really quite unique. And so here, what we target is this ring exchange Hamiltonian, which is very relevant to many interesting models. So for example, lattice gauge theories that we've heard quite a lot about, and then spin liquids, which we've also heard quite a lot about, and then other topological phases. So essentially on this hexagonal plaquette, you have two orders, like Z2 and Z2 prime, and then you oscillate between the two, also kind of like benzene, if that's a useful analogy. And this we can engineer, you could engineer directly. It turns out to be a bit nicer to engineer the three-body term, and then you get this six-body term to second order in perturbation theory, but crucially it's now second order, not sixth order. And you can also tune the strength of that by tuning both the two and three-body terms independently. So okay, if you engineer this, then you see starting from one order, you oscillate to the other and then back. And then simultaneously, the Hamiltonian also has two-body hopping terms. So you can see that, for example, if you just seed a single spin on this ring. And now the crucial thing to note is that this six-body interaction and the two-body interaction are happening on similar timescales. So this is very different to what you would get, for example, from just like perturbative hopping from a Hamiltonian, where you're restricted to this difference between sixth order and second order in perturbation theory, and is kind of pretty crucial. And okay, one example of like where you can start to use this six-body resonance is in stabilizing an RVB state or kind of just a GHZ state on this on a single hexagon. And the experiment that we do here, you adiabatically prepare kind of Z2 plus Z2 prime just with a sweep. Then you can either hold at some large static detuning where your system is now subject to various dephasing from whatever fluctuations you have in your experiment. And then you can compare that to what happens if you instead drive with Floquet, which then like induces this ring resonance and can stabilize the state against some of these dephasing mechanisms. And if you then adiabatically try and unprepare the state, depending on how well you return to kind of the all zero ground state, tells you how well you kind of stabilized this superposition. And you can see that in the Floquet case, you kind of pretty well return back to your initial state, whereas without it, you have some significant excitation probability, so showing kind of that you do stabilize the state by driving. Okay, so then as an outlook, we have this ability to do programmable simulation of many body systems, particularly generating dynamics, which is where we believe these quantum simulators really have power, and here very nicely with few global controls. Also starting to combine with digital tools, and kind here we, for example, use the programmable state preparation, but you can also think about using things like erasure detection and fast cycle rates. And then you can use these for probing these very complex many-body systems. So for example, lattice gauge theories, where now the 6-body resonance is your gauge dynamics, the 2-body hopping is your charge dynamics, and then the blockade constraint very naturally gives you the gauge constraint within your lattice gauge theory. And then Simon talked about the escape-based approach. So there you start to have this full Hamiltonian control. And you can also then think about in future, like this error-corrected simulation, and like what other applications can we use these simulators for? So for example, sensing, or error-corrected computation, simulation, and all kind of based on this very programmable platform. And I guess, then to thank the team, and then Simon, who's here, Naz, who is here, and who has a poster tomorrow, the many theorists, and the many experimentalists in our group who always provide stimulating discussion. Yes, thank you.
Questions?